This lecture, we're going to talk some about Newton's third laws. And Newton's third law is one of the more interesting of the three laws because unlike the first two laws, which only deal with individual forces on individual objects, Newton's third law actually talks about objects exerting forces on each other. We get to talk about interaction for the first time. So let's start with stating what it is. So the law reads, every action has an equal and opposite reaction. Now this seems like an incredibly vague law. For instance, what would be the equal and opposite reaction of eating a Big Mac? It seems like the equal and opposite reaction might have something to do with a scale on a toilet. But really, that's not actually the case here. When we say action, we actually mean is exerting a force. So a better statement might be, every time you exert a force, there is a force exerted back. So let's take the example of you're once again trying to slide a crate of bricks. Maybe you've taken up occupation as a bricklayer or something. So there's this big heavy crate of bricks, and you've really got to push on it. And you notice that your arms are getting tired and there's pressure on your hands. What's going on? You feel a force on your hands, but where is it coming from? You're pushing on the bricks, and it almost feels like the bricks are pushing back. And that's because they actually are. The bricks themselves are exerting an equal and opposite reaction. You're exerting some force on the bricks, and the bricks are exerting a force on you. Now, why don't you go flying backwards? Isn't that what F equals ma would tell us? Well, hang on a second. Your feet are also pushing backwards against the earth. And by every action has an equal and opposite reaction, the earth is pushing forward against your feet. So what does that mean? Well, the net force on you, the force that we're worried about, cancels out to zero. There's a forward force, a backward force, and they add up to zero. The force on the bricks, however, doesn't. You're exerting a forward force on them. There's no backwards force, so the bricks actually start sliding. And then once the bricks start sliding, you can walk forward again and do it all over again until you finally get the bricks wherever it needs to go. Now, it's very important to remember that the third law talks about interactions between objects. It's really easy to get sidetracked and start applying all the forces to the same object. And then you end up with paradoxes where things seem impossible. For instance, imagine a cart being pulled by a horse. The cart has some weight, some mass, and it's being dragged by this horse, and so the horse has to exert a force on it. But wait a second. We just said every action has an equal and opposite reaction. So if the horse is pulling on the cart, then the cart must be pulling backwards on itself. Equal and opposite reaction, right? And it would seem like that, but once again, no. And here's where we ran wrong. Even though it's tempting to say we have a force going forward, equal and opposite reaction, force going backwards, it all cancels out to zero, cart doesn't move, we have one too few objects in the system. Let's introduce the horse again and see if we can do better. Because what we said about this law at the very beginning of the lecture is that this is a law that interacts between objects. So we're actually going with a guy pulling this because I can't draw horses. And he exerts a force forward on the cart, and the cart exerts a force backwards on him. So there are two forces, and they are in opposite directions, but they're not on the same thing. So the cart can move, and if he's standing on a sheet of ice, he'll just go sliding backwards. But if he's standing on something with a little more friction, grass, concrete, really anything, then he'll be exerting a backwards force on the turf, which will exert a forward force on him. So once again, we can do equal and opposite reactions here. And the reason we can do equal and opposite reactions is the equal reaction goes on one object, and the opposite reaction goes on the other. And that's very, very, very important. And you'll see problems later on involving things like pulleys, where a block is weighted over a pulley, and then it's connected to another block that's sliding across a table or something. And what you find out is, as the one block slides down, the other one slides over. They're undergoing equal and opposite reactions. This block is pulling down or sideways on block B, and then block B is pulling up on block A. And that's why when the two things are connected, the one doesn't fall as fast as it would as if it was on its own, and the other one doesn't stay stationary like it would if it's on its own. That's a pretty advanced application of Newton's third law. We won't expect you to do that quite yet, But it's good to keep in mind generally how these rules get applied. And the thing to keep in mind for this specific rule is when you're applying equal and opposite reaction forces, always apply them to separate objects.